So suppose that I wanted to determine the value of this integral. Now this integral is a little bit different from other examples that we've done, and you'll see why if you do the thing that you're always supposed to do when doing these problems. If you look for the poles and graph them in the plane. So I'll have problem points at 3 and -2. And the problem, of course, is that my integration goes through my singular points. Now that, of course, is a problem. I need to say what I mean by that in order to get a meaningful result. That's the reason for this bar through the integral. That's intended to indicate that we want the Cauchy principal value of this integral. We're looking for the limit as epsilon tends to 0 from above let me write the other limit also, of the limit as delta tends to 0 from above of the integral from -infinity to -2 minus epsilon sine x dx over x squared minus x minus 6 plus the integral from -2 plus epsilon to 3 minus delta sine x divided by x squared minus x minus 6 plus the integral from 3 plus delta to infinity. Sine x dx divided by x squared minus x minus 6. All right? So the Cauchy principal value is indicating that we are to take these singularities symmetrically. All right? You go symmetrically toward the singularity. Now, that is going to give us a well-defined value for this integral. So what I'm going to do is make a closed loop integral. Okay? I can do that in a number of different ways. Of course, it's obvious that I'm going to need to add an arc at infinity. If I view this as the imaginary part of e to the ix divided by x squared minus x minus 6, then I can close in the upper half. I sort of like it without the limits, so I'm going to write it without the limits. All right, it's just from minus infinity to plus infinity. All right, so I can close this in the upper half plane. But now, I mean, this is still not a closed loop integral. I still have to consider the behavior in the vicinity of the poles. Now, the exponential isn't going to give us a problem near the poles. So we could choose to close below or above. And we could do that independently on those two poles. But of course, with an eye towards ease of computation, we might choose to close both of them on top. Because if we do that, then the loop integral contains no poles, and the loop integral will be 0. Now, we should not confuse that with the integral itself being 0. The integral does not equal the loop integral. At least not unless we can show that the arcs don't contribute. Now, the semicircular arc at infinity, the purple arc, we already know that that doesn't contribute in the limit as r tends to infinity by Jordan's lemma. But Jordan's lemma doesn't say anything about these two pieces. So our loop integral of e to the I z divided by z minus 3 times z plus 2 dz is equal to our integral I, and then plus these two little semicircles. All right? So what are those two semicircles? Well, this first one sees z as negative 2 plus epsilon e to the it. T will go from pi to 0. Okay? All right, z is negative 2 plus epsilon e to the it. So I'll have e to the I negative 2 plus epsilon e to the it divided by negative 2 plus epsilon e to the it minus 3 times epsilon e to the it, because it was z plus 2. And then I need my differential element, I epsilon e to the it dt. And then we have something very, very, very similar for the other contribution. All right, we're doing z minus 3. So that's going to be delta e it in the first piece, and then z plus 2. All right? So now let's simplify this and see what happens. As epsilon and delta tend to 0, look what's happening here. The reason that they were singular points, the reason that we're going through all these machinations, is because the denominator is vanishing. But that vanishing denominator is checked by the vanishing length of the circular arc as epsilon tends to 0. So once I cancel out epsilon e to the it, the danger's all gone. I can take epsilon to 0 with impunity, at will. And that makes for a far simpler integrand. If epsilon tends to 0, this is e to the minus 2i, I, dt. If epsilon tends to 0, this is negative 5. Okay? So it's going to be minus I e to the minus 2i over 5. Integral from pi to 0 dt. Same thing here. Delta e to the it cancels away. Here I'm going to get plus I over 5 e to the 3i integral from pi to 0 dt. And as we said, the loop integral itself, when we add all of these things up, contains no problems. So I get 0. Therefore, I, which remember was this piece, I start to take the imaginary part. I is equal to, both of these integrals give negative pi. So it's going to be I pi over 5 times e to the 3i minus e to the negative 2i. So that means that our original integral is equal to the imaginary part of this. So that's going to be pi over 5 times cosine 3 minus cosine 2. All right?